Okay, so we are going to look at an analysis of the SOR method. And again, it is the spectrum of the iteration matrix, or at least the spectral radius of the iteration matrix that really controls the story. So that's what we're going to look at. So let me remind you that for the SOR method, then the matrix, the iteration matrix, the T matrix that we call it, is D plus omega L inverse times 1 minus omega D minus omega U. Okay, that is the iteration matrix. And of course, when we implement the iterative method, the SOR iterative method, we don't actually ever compute inverses. We just solve systems of equations or even do something different. We went through a lot of different ways we could implement the matrix vector multiplication in one of the labs. Now, what we want to do is we want to connect this to we want to connect the spectral radius, or really the eigenvalues of this iteration matrix, to the eigenvalues of the corresponding Jacobian iteration matrix, which is D inverse U plus L. Remember the iteration matrix for the Jacobi is D inverse R, where R is equal to U plus L. Okay, so hold on 1 second here. I had the wrong set of notes, and there's a technical piece here that is going to be easier if I just have the notes correct in front of me. Oh wait, I think these are the correct notes. What in the world? Okay, and this is the iteration matrix for the SOR. This is the iteration matrix for the Jacobi. So what we want to do is show how we can relate the eigenvalues of this matrix to the eigenvalues of this matrix. Because typically, the eigenvalues here might be easier to compute than the eigenvalues here. I mean, this is just a much more complicated expression than what we have here. And so here's what we're going to do. We're going to look at what it means for something to be an eigenvalue of this matrix. So let me kind of give myself enough room to do this. What does it mean for a number to be an eigenvalue of this? Well, just by definition, it means there's some vector x, so that tx is equal to lambda x. Okay, so what we're going to do now is just write out what t sort is. It's going to be this. So we're going to have D plus omega L inverse times 1 minus omega D minus omega U x equals, and there's a reason I'm giving myself a lot of room here, equals lambda times x. Because what I'm going to do next is I'm going to multiply both sides by D plus omega L. And so this is the same as this. Okay, so now what we're going to do is we're just going to expand both sides. And when I expand both sides, what I'm going to get on the left-hand side is 1 minus omega dx minus omega u x. And on the right-hand side, I'm going to get lambda dx plus lambda omega L x like this. Okay, and we're now going to gather things and move them around a little bit. This is the, we're going to get we're going to organize things in terms of the D matrix. So we're going to move everything with the D over to this side. Or actually keep everything with a D on that side. Or move everything with a D to this side over here. And so what we're going to have on the left side is minus, this is going to stay on the left side, minus omega ux minus, we're going to move this over, lambda omega lx. And then what are we going to have on the right hand side? Lambda plus omega minus 1. So lambda plus omega minus 1 times dx. Okay. Now, what we're going to do over here, notice that there is an omega in each one of these and a minus sign. So we're going to factor out a minus omega. So we're going to have a minus omega. And then we're going to have a ux plus lambda lx. And in fact, what we're going to do, there's an x in both terms here, so we're just going to factor that out on the right. So we're going to get u plus lambda L times x. And then what we're going to have on the right-hand side is lambda plus omega minus 1 times dx. Okay. Now, let me make sure I've done everything correctly here. Because if I haven't, I need to see where the error is now. Okay. Very good. So here's what we're going to do. Now, there is maybe the computations up to this part, you can sort of understand why we're doing them. I think it kind of makes sense. But what I'm going to do now is I want to make this look a little bit more symmetric with respect to that lambda. So what I'm going to do here, on the left-hand side, I'm going to factor out a lambda to the 1/2, which means here I'm going to have a lambda to the minus 1/2, like this. And then if I factor out a lambda 1/2 here, I'm going to have a lambda to the 1/2 there. Now, I want to try to get something that looks like an eigenvalue eigenvector equation. So what I'm going to do is I'm going to divide both sides by minus lambda to the 1/2 times omega. And over here, we're going to have this divided by minus lambda to the 1/2 omega. And now I'm going to multiply both sides by d inverse. And since d is a diagonal, well, not since d is a diagonal, since this is a scalar, matrix vector multiplication commutes with it. So I'm going to multiply on the left by d inverse. And this is what we have here. Okay, so an obvious question is, why does this help us? And let me make this look a little more clear over here. Okay, the question is, how does this help us? Well, it is completely non-obvious how this might help us. But what is true is the following. This matrix right here, if we look at the Poisson matrix, if A is equal to the Poisson matrix, if A is equal to the Poisson matrix, then if A is equal to the Poisson matrix, then this d inverse lambda to the minus 1/2 u plus lambda to the 1/2 L is similar to this. Okay, so in the case of the Poisson matrix, this right here is similar to this, which is just the iteration matrix for the Jacobi iteration. Okay, so that's the case of the Poisson matrix. Now, it actually, and so what does it mean when we say, what's one of the things it means when we say two matrices are similar? It means they have the same eigenvalues. So in the case of the Poisson matrix, this thing that I've just circled here, the left-hand side, has the same eigenvalues as the iteration matrix as the Jacobi iteration matrix applied in the Poisson setting. Okay, well, it actually turns out that most of the matrices that we encounter and might want to apply these iterative methods to, they might not be similar to these matrices, but the spectrum of these matrices are independent of lambda. In other words, for many of the matrices that we're interested in, the spectrum of this method, the spectrum of this matrix right here is the same as the spectrum of this matrix. Okay, so let me say that one more time. For many of the matrices that we encounter, in particular the ones associated with the PDEs that we're looking at, the spectrum of this matrix right here is the same as the spectrum of this matrix. And the idea is that we sort of can compute or get a good idea of what the spectrum of this matrix is. So what does that say? It says, okay, if lambda is an eigenvalue of the iteration matrix for SOR, it says that this right here is an eigenvalue for this matrix, but we know all the eigenvalues for this matrix are eigenvalues for this matrix. So in other words, this right here, this quantity right here, has to be an eigenvalue for this iteration matrix right here. So let me summarize that. So I'm going to erase everything, or not everything. If lambda is in the spectrum of the iteration matrix for the SOR, and really like this, I'm just going to sort of emphasize that the spectrum depends on the relaxation parameter omega, then there is a mu in the spectrum of the iteration matrix for the Jacobi matrix, where mu is equal to lambda plus omega minus 1 divided by minus lambda to the 1/2 omega. Okay, and again, the reason is the spectrum of this matrix that I have circled is the same as the spectrum of this matrix. And we know that this thing right here has to be in the spectrum of this matrix because this is just the matrix times vector equals scalar times vector. Okay, so this has to be in the spectrum of this matrix, but the spectrum of this matrix is the same as the spectrum of this matrix. So that means there has to be some eigenvalue in the spectrum of this matrix where this is satisfied. Okay. So what we're going to do now is we're going to write this a little cleaner. And so we're going to square both sides of this and move all of this over here. And when we do that, we're going to get lambda mu squared omega squared. Okay. When you square this, you get lambda times omega squared. And then on the right-hand side, you're going to get lambda plus omega minus 1 squared. Okay, so this is the way that we can relate the eigenvalues mu of the iteration matrix for the Jacobi iteration to the eigenvalues lambda for the iteration matrix for this SOR matrix with parameter omega. That says how they're all related to each other. Okay, now if we look at this, the idea here, what we want to do is use this equation to try to get some information about lambda. Okay, because remember, the spectral radius of the iteration matrix is going to tell a story. It's going to control how fast the method converges, and we need the spectral radius to be less than 1. And in fact, if we can get a good estimate on it, that's going to let us know how many iterations. That's going to help us estimate how many iterations we need for the method to converge. Okay, or for the method to get within the tolerance that we have assigned. Okay, so if we look at this, and we square, if we square this and rearrange things, we can write this as a quadratic in lambda. We could also write it as a quadratic in omega, but we're going to think about this as a quadratic in lambda. In other words, given an omega and a mu, what are going to be the corresponding eigenvalues? And when we do this, we get the following. We get, oh, by the way, this right here is called a Young's equation. Okay, we get lambda squared plus lambda. This is just algebra right here, but I don't want to do all of the steps, and I don't, have it memorized. Mu squared, omega squared, plus omega squared, omega minus 1 squared is equal to 0. Okay, so what we have here is, again, it is a quadratic in lambda. We can see it as a quadratic in omega or a quadratic in mu if we wanted to, but it's a quadratic in lambda. And notice that as mu increases, in absolute value, especially if you think about omega as being greater than 1 here. For omega greater than 1, that's how we speed up the iteration. For omega less than 1, that's how we slow down the iteration. But what's going to happen is that if we think about, there's two solutions for this in lambda. For every fixed mu and omega, there's a quadratic, so there's two solutions. Either one repeated or two distinct. There's two solutions here. And as omega gets bigger and bigger and bigger, the larger solution is going to get bigger and bigger as well. As mu gets bigger in absolute value, the larger solution is going to get big in absolute value as well. So the lambda that is going to, so the mu that's going to give us the biggest lambda is going to be the spectral radius of the iteration matrix for the Jacobi method. So again, the idea here is that I want to figure out how I can bound lambda. So there's two things I need to do. For a fixed omega, I need to figure out what mu is going to give me the biggest lambda, and then that is going to give me an estimate for the spectral radius of the SOR iteration matrix. Okay, and on top of that, I need to figure out which omega is going to give me the optimal lambda. Okay, so here's what I want to do. I'm going to rewrite this equation, and I'm going to call rho j the spectral radius for the Jacobian matrix. And for a given parameter omega, the eigenvalue of Tj that's going to give me the biggest lambda eigenvalue is going to be the biggest eigenvalue and absolute value of the Tj matrix. So what it gives me is an equation like this: lambda squared plus lambda times 2 omega minus 1 minus rho j squared omega squared plus omega minus 1 squared is equal to 0. Okay. Okay, so now rho j is fixed, and now the question is, what omega now is going to give me the best lambda? So what omega is going to give me the best lambda? And so one thing that we can kind of do, there's a number of ways that we can think about this. One way is that we can think about lambda as being a function of omega. This is sort of implicitly defining lambda as a function of omega. Okay, and if you plot this, what you're going to see is something that looks roughly like something like this. I forget how it comes together over here now. Okay, but the point is, for every omega, we're going to get two different lambdas, a smaller lambda and a bigger lambda. The only time we don't have a smaller lambda and a bigger lambda is when omega is selected so that the two repeated roots actually become, the two distinct roots actually become a repeated root. Okay, if we have any other omega, we're going to have a smaller value and a bigger value of lambda, and that value of lambda is going to be whatever, the value of lambdas over here are going to be bigger than that value of lambda. Okay, so the idea is that we want to find the omega for which we have a repeated root. Well, what is that? So we want to find the omega for which we have a repeated root. Well, it's just going to be when the discriminant of this is equal to 0. So it's going to be when the square root of b squared, which is 2, times omega minus 1, minus rho j squared, omega squared, b squared minus 4ac, when this is equal to 0. And of course, we can square this, and now as it is a quadratic for omega, when you solve this, you're going to get one value for omega that's greater than 2, and the other value for omega is going to be the following. We call it omega optimal because it gives us the optimal value of omega. This is equal to 2 divided by, divided by 1 plus the square root of 1 minus rho j squared. Okay, so again, what this is saying is that if I have a specific matrix, again, one that satisfies this weird property where the spectrum of this matrix with the lambda is the same as the spectrum of the TJ matrix. All of our matrices satisfy that, even something a little bit stronger. It says the following. It says that if I want to find an omega, if I want to find an omega that's going to make the biggest eigenvalue of this matrix as small as possible, this is what I want omega to be, where rho j is the spectral radius of the Jacobian matrix. Okay, and now from this we can figure out what, sorry, hold on a second. And now from this we can figure out what the optimal value of lambda is. And if we know what the optimal value of lambda is, we know what the spectral radius of lambda is. So in other words, what I'm saying is, if we want to know what the spectral radius is, we're going to take this value for omega, plug it into there, and then compute what lambda is equal to. But remember, the whole point is that the discriminant is equal to 0. Okay, omega is selected so that the discriminant is equal to 0. So if we want to look at the like the quadratic formula, well, it's just going to be lambda 1 and 2 is going to be equal to minus b divided by 2. 2 times a. And this is what minus b is there. And you can put that in, you can put this formula in for omega and compute it to tell you what that lambda is going to be. And then in the lab videos this week, we're going to see how we can apply these ideas specifically to the Poisson matrix and get some very sort of precise estimates on the spectral radius for the Poisson matrix. And it'll be a lot of fun because we're going to use it like Taylor series several different times and a lot of sort of estimates that really are sort of just very common tools in areas like this. Anyways, but we're going to do that for the labs because that's basically what the homework is.